Now that we know that the only way you can determine an electron's location is to hit it with a photon, we have what we call scatter plots of electrons being hit by photons. This is just one single electron that's found after being hit by a photon several thousands or millions of times. You see that there's two different shapes. This region where an electron is 90% likely to be found around a nucleus is called an orbital. Here's what the scatter plot on the left would look like if we drew it as if it were a cloud of electrons. So I'm going to describe orbitals in 4 different ways. The first way I'm going to describe is size. Now this is also known as the principal energy level or a shell. Now the reason why it's called the principal energy level is because the electrons that are spinning around this nucleus are attracted to the protons in that nucleus. So in order for them to get away from that proton, they probably are moving much faster or with much more energy, and the more energy they have, the further they can get away from the nucleus. So if you see in the number 1, that has the principal energy level of 1, meaning that electron doesn't have much energy, so it doesn't get a path very far away from the nucleus. In the one in number 3, principal energy level 3, it will actually have enough energy to get very far away from the nucleus in its path. So the first way to describe orbitals is by its size, which we will give numbers 1, 2, 3, and they can go up to 4, 5, 6, 7, and so on, as long as the path of the electron keeps getting larger. The second way to describe orbitals is its shape. Now another name for shape we call sublevels. As you can see, there are 4 different sublevels. Now remember, this is just depending on the shape. There's the S, the P, the D, and the F. Here's a way to help you remember the shape of each one of these orbitals. The S is spherical, so all S sublevels are spherical. The P's are shaped like dumbbells. You can remember that by remembering pumping iron. All the paths of an electron in a P sublevel have that shape. The D looks like a daisy, and the F kind of looks weird. The third way to describe orbitals is orientation. And what you see here is I've got 3 different orbitals on the 2p sublevel. So the 2p sublevel represents 3 different orbitals based on their orientation. So you could have electrons traveling in the path on the x-axis, like in the top left there. You could have them traveling on the y-axis, like on the top right. And you can have them traveling on the z-axis on the bottom one. So as you can see, in the 2p sublevel, meaning it's got a principal energy level of 2 and it's going in a dumbbell shape, there's 3 different orientations that you can have. So there are 3 different orbitals in the 2p sublevel. Remember that for later. The last way to describe an orbital is its spin. The electron can either be spinning clockwise or it can be spinning counterclockwise. There are 3 basic rules you need to follow when you are describing the quantum mechanical model of the atom and its electrons. The first is called the Aufbau principle, or the diagonal rule. This tells us what order the energy levels go in. Now before we get into that, let's look at how many levels there are for each principal energy levels. Notice there is only 1 sublevel in principal energy level 1, 2 in energy level 2, 3 in energy level 3, 4 in energy level 4, and principal energy level 5 could theoretically have 5 sublevels. What we see here are the size of the orbitals and their shape. It doesn't tell the orientation or the spin of the electrons. Notice in 1s, it is a very low energy electron and it's moving in a spherical pattern. If we move up to 3p, it has a much larger path and is moving in the dumbbell type pattern. Electrons will increase in energy level in the following manner. The first level they come to is 1s. The second level they come to is 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 4f, 5d, then 5f. If you can write out this diagram and perform the diagonal rule, you'll be able to see the order at which electrons increase in energy. The second rule of atomic orbitals is the Pauli exclusion principle. Here I have just one orbital, the 2s orbital, meaning it has a mediocre size path and is moving in a spherical pattern. The Pauli exclusion principle tells us that you can only have 2 electrons in one orbital, and when they are in the same orbital, they are moving in opposite directions, meaning one is going counterclockwise and the other is going clockwise. Because of this Pauli exclusion principle, and we know we can only have 2 electrons in each orbital, knowing the number of orbitals we can have in each sublevel, we can determine how many electrons are in each sublevel. The s can only have 1 orbital, and it has 2 electrons. The p has 3 different orbitals, thus giving us 6 electrons. The d has 5 orbitals, giving us 10 electrons, and the f has 7 orbitals, giving us 14 electrons. The third rule of atomic orbitals is Hund's rule, or what I like to call the stinky bus rule. This essentially tells us that electrons will go to equal energy orbitals until they all have at least 1 electron in them, then they will go back and counteract spin. Here's an example. In the 2p sublevel, we have 3 orbitals, the px, the py, and the pz. The electrons will fill in this order. 1 in there, 1 in the py, 1 in the pz. Now that they're all full, they will go down, down, and down. Notice we did not go back and pair up electrons until each equal energy orbital already had an electron in it. So as a recap of your 3 rules of atomic orbitals, we have the off-ball principle telling us the order at which electrons are filled in energy levels. We have the Pauli exclusion principle stating that you can only fit 2 electrons in one orbital and they have to counteract spin. And we have the stinky bus rule, or the Hund's rule, telling us that you have to fill equal energy orbitals before you go back and pair up.